So the next section we're talking about is how data types influence certain measures that we have in statistics. So a simple table here, I have the 4 data types as 4 columns, and I have 3 very simple statistics that all of you already know, the mean, median and mode. And let's take a look at how data types plays a function here. Mode simply means how many times has a quantity occurred and which has occurred the most. So you can do that for a nominal, you can do that for an ordinal, interval and ratio. All 4 data types you can calculate the mode. But in case of calculating the median for a nominal data type, it's not possible. We can't really order my data values, so I can't really find the median of a nominal. But it is possible for the ordinal, since we can arrange the ranks of the values from ascending or descending order, and the median being the middle value. Interval and ratio, pretty straightforward. You can find out the median temperature, you can find out the median height of people. So those are 2 examples where both of them would work. And as far as the mean or the average, neither nominal nor ordinal would be capable of being computed. Even if it wouldn't make mathematical sense. So the only place you would apply a mean is if your data was interval or ratio. And going ahead with this course, I'm going to be referring to the data types as either numeric or categoric. Numeric data types are interval and ratio, whereas categoric data types will be broadly referred to by nominal and ordinal data types. And the mean, median and the mode collectively are known as the measures of central tendency. A little limitation of working with means. You could take a look at these 2 sets of numbers. I have 80, 70, 60, 50, 40 and 5 values of 60. And if I were to ask you what the mean is, it's the same irrespective of which data set you look at. So the problem we have is if you are reporting the average value of some quantity, you could be grossly misleading your audience. Telling me that both these classes have performed with an average of 60 actually is half the story. We can see that one class has people who have even reached 80%, but the others have hit only 40%, whereas the other class, everybody is consistent at 60. So there's 2 different stories, and we'd like to tell the story a little better. And to do this, we have 2 measures. We have standard deviation and variance. Again, 7th standard high school mathematics, nothing new. But the purpose of using a standard deviation is, as this graph depicts, standard deviation is simply the spread of your data around the mean. If the data is more spread out, as in the first example in the previous slide, you would have a higher standard deviation. If the data points are closer together towards the mean, your standard deviation will be low. So your formula, standard deviation formula, which is visible here, take a look at it a little closer. So we have under the square root sigma of x minus x bar whole square. Sigma of x minus x bar simply meaning the summation of the distance between each point from its mean. We take the square of it and we divide it by n minus 1, adjusting for the fact that standard deviation makes sense only if you have more than one observation. Right? We take the root of that, and that's your standard deviation. Variance is the same formula, except I don't use the square root. They have different purposes, and we will explore that a little later in the section. But for now, standard deviation and variance together are known as measures of dispersion. And this is where I'd like to slip in a little new statistic, something you probably might not have heard earlier. This is the standard error. The math behind the standard error is very simple. It's simply standard deviation divided by root n, where n is the number of observations in your sample. Why would I want to care about a standard error? Right? A very simple question. Why would I care about a standard error? So let's take a very simple example here. I have 2 people carrying out a survey for me. I want to find out what is the average height of people in a city. So the first person doing the survey goes out for 5 days in a row, asking 10 people each day, what is your height? And at the end of 5 days, he's got 50 observations, and he reports that the average height is 5 foot 5 inches. And you wonder, maybe so, maybe not, but knowing that only 50 people were asked, your confidence in that value is probably low. The second surveyor goes out for the same 5 days, but he asks 1,000 people every single day what your height is. And at the end of 5 days, he comes and reports that the average is 5 foot 5 inches this time as well. But if I ask you who would you have trusted more, you are likely to go with the second person, right? You have a sense that since he has more observations or his sample size is larger, the reliability of his estimate goes higher, right? So standard error is simply the measure of how reliable is my estimate of the population, right? And since we work with samples all the time, knowing how reliable your data is critical to your findings.